All right, we'll let that one just float away.
Wise choice.
So, let's see. So, electrostatics, the sort of fundamental equations we have for them allow us to look at a variety of solutions. And what we discussed is when you're faced with looking at you're given some charge distribution, you want to find the fields or the potentials associated with that. Want us to think a little bit about the best approach to doing that. As we discussed, there is a general formal solution that relates the charge distribution to the potential, but depending upon the symmetry of the problem, you might want to approach the problem sort of through the back door by first using Gauss's law to get the field, and then using the integral of the field to get the potential. Or if you can't use Gauss's law, well, to get the field, you would find the potential and take the gradient to get the field. You have to think about what's the best approach for doing that. Okay, so that's the general kinds of problems that we're faced with. Quite often, we're looking at circumstances where we won't necessarily specify just the charges, but we will specify that there are some conducting materials around. Of course, if we knew what all the charges were in that material, well, then in principle, that solution is here. But in practice, we don't necessarily know that, and in fact, that may not be the most efficient thing to do. We'll remind you of a particular example of that in a moment. So the conductors, we're thinking about them as perfect conductors, and many materials, metals, are well approximated by perfect conductors, ideal conductors. And some of the important properties that we discussed, that we mentioned last time, is that the electric field inside the bulk of a conductor in electrostatics is zero, and whatever free charges there are, if there are any, they reside at the surfaces, and those surfaces are equipotential surfaces. Okay? So, what that means is that quite often problems, this chapters 2 and 3 of Jackson are all about solving for the electrostatic potential in the presence of conducting boundary conditions. It's often a problem we care about from practical considerations. So formally speaking, we can solve that problem by saying, well, the general problem is the Poisson equation, and we want to look for solutions to Poisson's equations that include both the particular solution and the homogeneous solution. So now Lagrange's function is more general, where the function f here is a solution to Laplace's equation, and it's chosen in such a way that the boundary conditions set by typically conducting surfaces are satisfied, because we said conducting surfaces define are equipotential surfaces. So the general solution, formally speaking, is of this form, involving the convolution of the source, if there are free charges other than the ones that are part of the conductor, with this Green's function, and that function again, f again, will depend on the geometry of the boundaries, and then generally a surface term. Okay, and if we have no sources, we only have the potentials and surface charges on the conductors, and this term is 0. And then we have the standard kind of boundary condition whereby one specifies either the potential everywhere on the surface, so-called Dirichlet boundary conditions, or in other places, we specify the normal derivative of potential on the surface. And by some manipulation, one can show that the solution to Laplace's equation is uniquely specified. That is to say, there is one and only one solution which can satisfy those boundary conditions. So specifying the boundary conditions alone specifies this in the absence of sources, and if we have sources, then we add this term as well. Okay? So let me remind, yeah, please.
Isn't a boundary condition something mostly these from Dirichlet and Neumann?
That's right. These are the Neumann, I'm sorry, these are the Dirichlet boundary conditions if you specify the potential everywhere. The Neumann boundary conditions are if you specify the normal derivative everywhere. And then mixed boundary conditions if in some regions you specify potential and some places you specify.
It has a different name here?
No.
Oh, okay.
I said these are the Dirichlet.
Okay.
I just forgot to say these are the Neumann. Right? I mean, if I specify this everywhere, I can't specify both. That actually, there's no, I can have a conflicting solution if I have both. I can have in some regions the potential, in some regions normal derivative, but I can't specify both those things and have a unique solution. All right. So an example, a simple example that I'm sure you've all seen is the problem of looking at, for example, suppose I have as the problem, I have a circumstance where I have an infinite conducting plane that's grounded, and above it I have some charge density. Okay? And I want to specify, let's say this is the plane z equals 0, and I want to specify the potential everywhere for above the plane. Okay? How would you do it?
Image charge.
Image charges, right? Because, well, the point here is that what's going to happen, of course, is if, say, this is positive charge, I'm going to attract, there's going to be some, negative charges that are going to be attracted to where the positive charges are, and positive charges on the away from, repelled from these guys. There's some surface charge distribution. If we knew all those charges, well, then we could, just integrate and find it. But that's generally not what we would do, because it's a waste. We could figure it out, actually, but we could write down a solution almost instantaneously, as was suggested, based on the method of images, because of the uniqueness property of the solution to the Laplace equation. If we find any solution that satisfies the boundary conditions, well, that is the solution. Okay? And we can guess that solution just by the symmetry of the problem and our deep knowledge and understanding of the nature of these potentials. So, of course, here I had a general charge distribution. What I want to look at is the solution for a point charge. And then once I have a point charge, I can convolve the solution of a point charge with the general distribution to get the complete solution. Okay? Of course, I would, if this potential wasn't grounded but sent to some other thing, well, then I would have this term as well. But the surface term is 0 here because the potential is 0. So let's do the problem. So, method of images is a wonderful trick when it works. It's kind of like Gauss's law. If you could use it, use it. But very rare that you can use it. But this is an example, meaning that we could just guess the solution. So here's my, let's put this, let's call this the, oh, it doesn't really matter, the x-axis. Here's the charge, point charge. Here's my conducting plane. And I want to write down what is the solution for the point charge. If I know what the solution for a point charge is, then I know the solution for an arbitrary distribution because I just convolve that. So what's the solution? Well, the solution has to be something which satisfies the boundary conditions and satisfies the fact that there's a point charge here. And we can write that instantly if this is a distance d above the plane. We seek a solution with the potential at z equals 0 as a function of x and y is 0. And point charge at x equals, what do they call it, d. Well, the point charge q. If I put a equal and opposite charge, charge minus q, below the plane, then the field produced by this image charge above the plane is exactly the same as all these negative charges on the surface, because the combination of these two things makes a field that is normal, oops, it's negative charge, positive charge, to the surface. And as long as I produce a field that's normal to the surface, that's the solution. So it's not the solution below here, because below here there actually isn't any charge. But this point charge below the conducting plane mocks up. It produces exactly the same field above the plane as all the induced surface charges do. That's the point. Yes?
So what would be the solution below negative d? Would that be like a outpole seen from edge?
It's a much more complicated solution. In this case, I mean, the potential we know in this case, below here, there is no field. So what's happening here is that below, the induced surface charges combined with here are making no field, right? Because I can put a field at infinity here. The potential is 0 here, potential is 0 here. Therefore, the solution is potential is 0 everywhere. That uniquely satisfies the boundary conditions. Of course, that's like a Faraday cage, right? If you want to shield yourself from electric fields, go behind the conducting cage. It's a good place to hang out in a thunderstorm. So, but above, this is the solution. And here it is. And therefore, we know what the potential is for z greater than 0. The potential, which is not a vector, but that's a vector, is equal to q. So I'm going to set this to be a unit point charge. So I'll set q equal to 1. X minus d e sub x squared minus x minus x squared, or 1 minus x minus v squared plus y squared plus z squared, square root, minus x plus v squared plus y squared plus z. And this is thus the Green's function for the point charge, in this case, at position D in the x direction. Now, if I want to write down the general Green's function, I would just make this an arbitrary point, x prime.
What's the square?
Sorry? That's potential,
And what's the square?
because it should be there. Excuse me. Thanks. So, this is a case where you could just write down the Green's function. And then I would write, and the general Green's function would be square root of x prime squared y minus y prime squared plus z minus z prime squared minus square root x. The x coordinate is the same for the image, the y coordinate is the same for the image, but the z coordinate is minus the z coordinate. Oh, and then, oh, sorry, it's the x coordinate. The x coordinate, that's the opposite. Way I put it. Okay? And then I would just convolve this. Yeah, my plane here is not at z equals 0, it's at x equals 0. I apologize, I changed my coordinate system. All right? So, you glance, just for memory and a little bit of exposure, glance at chapter 2 and 3 of Jackson. Look at the Green's function for a conducting sphere, for example, or a charged ring or something. Just get a sense of what those things are like. All right? All right. So one last thing I wanted to discuss in relation to thinking about conductors, just to remind you quickly about the notion of capacitance. And so the notion of capacitance is the following. If I have some conducting surface, maybe I have another conducting surface somewhere, and I put a battery with a potential difference between them, then what we know is that charge will build up on each of these conducting surfaces. In order such that the potential difference between these two conducting surfaces is V, each one being an equipotential surface, because that's what we said. The surface of a conductor is an equipotential surface in electrostatics. Okay? And the capacitance is defined such that the charge, the equal and opposite charges that build up on these, the mutual capacity, if you like, between these two conducting surfaces is proportional to the voltage by a quantity C, and this is the capacitance is purely geometric. assuming in this case that we have vacuum and in between them, and this is a perfect conductor. So the capacitance is a property of the geometry of the conductors, and the geometry alone. So, how do you calculate capacitance?
Well, empirically, that's one way.
Or you can measure it,
Yeah.
yeah. But if you couldn't measure it, or you're not given the actual apparatus, you want to know what you expect. How would you calculate the capacitance?
On the potential distribution.
Sorry?
On the potential distribution.
From the potential, but what you're given here is that if you make a potential difference between these two conductors, then there will be charge. So how are you going to calculate what that potential difference is? Well, the problem is generally complicated. I mean, what we can do is we can solve, as Boyan was suggesting, we can solve this problem. I'm given what the potential surfaces are, and there's no other free charges other than the ones on the surface, then we can solve Laplace's equation. We know Laplace's equation, then we solve the potential, and then the normal derivatives to whatever potential we get must be related to surface charge density from the boundary conditions that we have. Remember, the field is zero inside the bulk, and it's got, this field outside. The discontinuity in the normal derivative is related to the surface charge, so we could do that. Now, we rarely actually do that. There's a few problems where we can calculate it because we have very symmetric circumstances. And we go around that triangle in a different way. So often when we're calculating capacitance, we're doing it because the system is so symmetric that we can just write down using Gauss's law. So typically, we find capacitance when there is symmetry. So, for example, the canonical example is the parallel plate. So in the parallel plate, we have two conducting planes, which are plates, which look kind of parallel. And we attach our battery to it and create a potential difference. And we want to find the capacitance. Well, what do we know? What we know is because of this problem, we know that this is an equipotential surface. But we know from the symmetry that the charge distribution that creates that equipotential surface is one if the charge is uniform. Because we know that a uniform sigma, surface charge density, is one which produces, for an infinite plane, a uniform potential on that plane. Because we've studied the problem of what potential is created by an infinite plane. So we know that what's going to happen in this case is that I'm going to get Q to the degree to which we treat this as approximately infinite. I mean, we'll get Q, but it'll be uniform, with a uniform surface charge density here and minus Q there. Now, it's not exactly true because of the fact that there are edge effects, but it's a good approximation, and as you're seeing in your homework, as long as the distance between these plates is tiny compared to the size of the plates, well then, it's a good approximation. Okay? So what one does to calculate capacitance of these problems is one puts uniform charge. If you know from the symmetry that the surface which is equipotential is the surface with uniform charge density, you put that uniform charge density down on the surface. And then you calculate the potential. And then the ratio between them is the capacitance. So now I ask you, what is, suppose I didn't have the boundary here and I just had two parallel plates with equal and opposite charge uniformly distributed on those planes. Each plane has an area A, and the distance between the planes is D. What is the potential difference between those two planes? Yeah?
Well, I mean, you can just, figure out what the charge density is, and then that tells you what the electric field is, and then you just integrate from.
Exactly. So in these systems where we have high symmetry, we use Gauss's law to determine the electric field from the given charge distribution. And then we integrate over a distance to get the potential. So what is the electric field associated with this parallel plate charge distribution?
Q over maybe 4 pi.
Maybe there's a 4 pi in there, right? We remember, right, if we looked at a single plate, if this had a charge distribution with a charge per unit area Q over A, and I make the little pillbox, which has a little, little a, and then for I have the flux integral E dot dA is going to be equal to 2E in the normal direction times A is 4 pi times the charge enclosed, which is equal to 4 pi times the little a times the charge, right? That's the charge enclosed, so that the electric field from a single plate is 2 pi Q over A, or 2 pi sigma. And if I have the equal and opposite guy over here, then it adds in between, and the outside goes to 0, to which fringe fields are negligible, right? So inside a parallel plate capacitor, the electric field is 2 times this, or 4 pi Q over A. Uniform. So what is the potential difference between those two plates? Well, it's the integral of E dot dl, but E is constant, so it's just E times the distance between the plates. I mean, that's something we shouldn't forget, the most basic facts. We forget oh my God, there's some Laplacian, I got a Green's function. No, I mean, the electric field is volts per unit distance, okay? So, and that's, oh no, we want the other thing, volt, right? So this is then equal to 4 pi d over A times Q, and the voltage is equal to Q over the capacitance. So the capacitance of a parallel plate is the area divided by 4 pi d. Purely geometric. Now, if in SI units, 1 over 4 pi is epsilon naught. So often in SI units, epsilon naught, the units of SI of capacitance in SI units are farads. So epsilon naught is often given in terms of farads per meter.
Whatever.
But in these beautiful set of units, capacitance has the units of geometry, because that's all it is. So capacitance in CGS units is units of centimeters, saying something about the ratio between the area of a capacitor to the distance between them. All right. Now, of course, a capacitor stores electrostatic energy, right? Because there is work done by the battery in moving charge between the conductors, right? So the work, if I have the parallel plate capacitor, as I'm charging it up, moving charge, and if I move a little bit of dq onto the plate, moving it from the other plate, then we know the work done moving a little chunk of charge dq is whatever the potential difference. It has to move it against whatever potential difference there is. And that potential difference, if there's a particular amount of charge already on there, is equal to Q over C. So if I were to integrate this to the final charge, that's 1/2 Q squared over C, which is equivalent to 1/2 CV squared. Okay. Now, of course, that work that we've done, as we discussed, that energy can be thought to be residing in the field. So this should be equal to the total integral over all space of the created electric field, over 8 pi. Let's check that. Well, the electric field is 0 everywhere except inside my tasty ice cream sandwich. So my electric field, and it's uniform, so I could just write it down as the electric field is 4 pi Q over A squared times the volume, this is over 8 pi, times the volume, and the volume is A times D. Okay, so that's then equal to, well, this is going, I don't know if this is the best way to do it, but we did it, I did it this way. 2 pi Q squared over A times D. Right? And we said so Q squared is equal to, should have done this in a slightly different way, but oh well. Q is equal to C times V, C squared V squared over A times root of 4. Where? Oh, yeah, 16. That helps. Thank you.
2 divided by 8.
Oh, wait, no.
Oh, no.
It's just,
Okay, yeah, because there's a half here,
yeah.
so it's gonna work. Right, so that's what we got. Let's plug in for C. So we got 2 pi C v squared. This is a mess. This was a stupid way to do it, but I did it. And the capacitance we said was A over 4 pi D, which is equal to times D, which is 1/2 CV squared. That'll work. There's better ways to check that. But indeed, the work done in moving the charge is equivalent to the energy stored in the electric field. All right? Okay. So, as we said, there are many, when we're dealing with problems of electrostatics, we have this whole bunch of methodologies, the methods of images, the method boundary conditions. What I'm going to concentrate on, because it's going to be very important for us in building our foundation for thinking about electrodynamics and radiation, is looking at the problem where we have approximate solutions for localized charge distributions without conducting boundaries. Okay? So the problem I want to look at, the general problem I want to look at is, suppose I have some distribution of charge, whatever it is, and we have some point of observation. Okay, so put the origin wherever I like. X is the point of observation. Here I am looking at it. And I want to know what is the potential associated and then the field associated with this charge distribution. Well, we know what it is as a general rule. We have the simple solution, integrate over all space. So we have each little chunk located at some x prime, and we have script dr, the distance between the source point and the point of observation. Okay? So what we want to look at is the case where the distance of observation is much, 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 much bigger than the distance from the origin to any other point in the source. We want to consider if there's some size here of the source. We want to look at the case in the so-called far field, where the distance to the point of observation is much, much bigger than the distance to the source for all x prime. Okay? Now, we know that solution in a simple case, if when we're far enough away from this, it should look like a point charge. So for example, suppose I have a ring of charge, a burning ring of charge. Okay? And it's uniformly distributed along that ring of radius A. And I want to find, say, the potential at some distance away. Now let's say I'm on the z-axis. Let's call the z-axis the axis of symmetry. Well, we know an exact form, in this case, at least on the on-axis. We can write down an exact solution for this, right? Because every point on this ring is the same distance from the point of observation. So the potential on axis is q over that distance. And that distance is equal to the square root of z squared plus a squared. If I were to integrate it as a little dq, I would just get every point contributing the same, because they're all the same distance from the point of observation. So that's the exact solution. Now, in this far field limit that we're considering, we're looking at the case where z is much, much bigger than the size of the distribution. In that case, we can do a Taylor series expansion of this, as we've done before. So the potential on the z-axis here is q over z. Well, let's write this down, q over z times 1 plus a squared over z squared to the minus 1/2 power, where the small parameter here is the ratio of a to the distance of point of observation. So we can do a lowest order binomial expansion. Write this 1 minus 1/2 a squared over z squared, or q over z minus q a squared over 2z cubed plus dot, dot, dot. Okay? So the lowest order, what we see is the expected term, the potential is just the potential of a point charge. If the distance along the z-axis is much bigger than the radius of this ring, then we can't see that geometry, and it looks like a point charge with total charge q. But then there are correction terms, which we're going to study their properties in more detail. In fact, this is a quadrupole correction to the monopole dominant part of this distribution. Okay? Another example. Suppose I have two-point charges of equal and opposite magnitude. Okay? Let's put the origin, just for ease, halfway in between. And there's some point of observation x. And so now the question is, what is the potential associated with these 2 point charges to lowest order? Well, you might say it's the, far enough away, it looks like the potential of a point charge. But the total charge here is 0. So that vanishes. In fact, we can look at this if, so this is my scripty r plus, and this is my scripty r minus, then the potential in this case is q over the magnitude of scripty r plus minus, this is the exact potential. But we want to look at this in the limit, if I call the distance between the two charges d, that the point of observation is much, much bigger than this separation distance d. Well, we can do that kind of instantly here. This is like, you know, the diffraction, double slit diffraction problem that you solve in freshman physics. If this is far enough away, then these look effectively parallel to one another. And then the distance between them, the difference between these distances is just this little piece, right? I write this as Q, the length R plus minus the length R minus divided by R plus times R minus. This difference in those path lengths is this. And if I call this angle theta, then this is d cosine theta. Or d sine theta. So this, and equal to q times d sine theta divided by these guys are about the same, r squared, where r is equal to the distance of the point of observation, approximately. Okay? So in this case, when we had no net charge, then what we see here is that the potential doesn't fall off like 1 over r at large distances. It falls off like 1 over r squared. It falls off more rapidly. In this case, the dominant term falls off like 1 over the distance of the distribution because there was net charge. And then if I have a net charge, then it looks like a point charge. That's the dominant term. And it falls off like 1 over the distance. But here the net charge was 0, and what we see is we get the potential falling off like 1 over r squared. This, of course, you recognize as an electric dipole. All right. So we want to characterize these things. Oh yeah, there's one other last example. So let's now suppose I have the following charge. Suppose I have two dipoles but those dipoles are oppositely oriented. Okay, so let's just make a coordinate system here. Put the origin here. Let's how do I define this? This is x, this is y. And the x and y coordinates of each of these guys are confused. So they're on a square with the plus and minus charges distributed on the corners of the sphere that way. Okay? So in this case, the potential, the exact potential, well, I have charge number 1, x minus d squared plus y minus d squared plus z squared. It's in the z equals 0 plane. And then I have this charge, which is minus q. And then I have x minus d squared plus y plus d squared plus d squared. And then, you know, the other two terms. So this is just writing down the exact potential. And we can do the same Taylor expansion, which I won't bore you with, for if my distance r is much, much bigger than d, then what we find is that the potential as a function of x, y, and z is equal to L, bless you, qd squared times the x coordinate of observation, the y coordinate of observation over r to the fifth, plus dot, dot, dot. And if I wanted to write this in spherical coordinates, which I want to, x is equal to r sine theta cosine phi, y is r sine theta sine phi. This is then equal to sine squared theta sine phi cos phi divided by r cubed. Okay, so what we see in this case is that this distribution has no net charge, so there's no 1 over r term. It also has no net dipole moment, as we will remind ourselves. You kind of see that because there's two dipoles that are oriented that cancel one another. So the lowest non-vanishing term has a potential that falls off like 1 over r cubed. It's not isotropic. Remember, theta, r theta, and phi here are the coordinates of the point of observation. This is saying something about how the charge is distributed in space, or charge is. And this dependence is characteristic of what we call a quadrupole potential. So what we're going to talk about today and for the next few lectures is this whole problem of multipole moments in electrostatics. Okay, to do so, let's return to the general expression for potential for an arbitrary charge distribution with no other boundary conditions and no charges at infinity, so that we can get infinitely far away in some limit, or very, very far away from the charge distribution. Okay, so I'm going to draw the picture again. Here's the charge distribution. Here's some particular point within the charge distribution. Here's the point of observation. And we have some distance, script r, between the point of observation and the point of the source. Okay? And we have the general expression for the potential. And our goal is to find some kind of general expansion, not some specific expansion that we had there for the Taylor's expansion, which shows a dominant monopole term, and then a next order dipole term, and then a next order quadrupole term, and then a next order octupole term, etc., etc.
No sextuple.
It's all two to the pole. All right. So, how are we going to do that? Well, this expression, this is where we have some comparison between the point of observation and the point of the source. And we are integrating that over a distribution which is localized in such a way that we're going to look at this for regions where x prime is small in magnitude compared to the magnitude of x. Okay, so r prime is equal to the magnitude of x prime is going to be much, much smaller than r, which is the magnitude of x, for all r prime at some r. Okay, so we're looking in this limit. So this is going to be a little bit of tedium, maybe a lot of tedium. Let's see how it goes. So let's do a little aside over here. Let's take a look at the Green's function.